Happy birthday week to me!
Our birthday week's a thing? And is this really how we're going to start this episode?
Well, I thought it was kind of appropriate because April is a special month, besides being my birthday month.
Somehow we've gone from birthday week to birthday month, but
Anyways, April is Mathematics and Statistics Awareness Month.
a couple of fields of which we are very aware.
True, but I thought we should do something to celebrate the holiday.
Math is the one where you're the most intellectually naked, which is terrifying until you can break through. I know my mathematical body is ugly and old and withered, but then I'm okay with it.
Whoa, Sadie, we try to keep Carry the 2 PG rated.
Don't worry, we'll keep this mostly nudity-free as we hear from today's guest about what mathematical research really looks like and how he approaches mentoring the mathematicians of tomorrow. Meet University of Chicago math professor Benson Farb.
And before we get to the good stuff, we should introduce ourselves as well.
Good call. I'm Sadie Witkowski.
And I'm Ian Martin.
And you're listening to Carry the 2, a podcast from the Institute for Mathematical and Statistical Innovation, aka IMSI.
This is the podcast where Sadie and I talk about the real-world applications of mathematical and statistical research.
We might seem like an odd couple to tackle these topics. I'm a cognitive neuroscientist, and Ian is a high school choir teacher.
But thankfully, we're going to Benson to explain mathematics research to us.
A thing I actually had to ask him about, even after working at IMSI for almost 2 years now. What does it mean to do math research?
Yeah, I think most people, including me, don't understand what it is. And so that's why they never even know there's something to go into. And one thing I always tell people is that the highest math level that 99% of people attain would be calculus, which is already a very high level. It's one of the great ideas of human history. It's very important, very sophisticated. It was basically what you learn is completely finished in 1700. And so we've been doing math is advanced like as much as physics or chemistry.
Somehow this makes me feel both better and more confused.
Yeah, I mean, it makes sense that what we teach in school is just the fundamentals of any particular subject, whether that be chemistry or mathematics.
Or choir. Like, you've got to learn the basics of how to read music and produce sound before being able to, perform an opera.
So somehow we have an easier time imagining what biology research looks like and what kinds of questions they're trying to answer. But I think we don't often enough apply the same filter to mathematics.
I think the most common misconception is that we're dealing with numbers or something to do with accounting, or that maybe it's not a misconception, but not realizing, they say, well, what else is there to learn? And I completely understand that. They're shocked that there are 500 journals. Each one, there's 100 new papers a day being created. 1,000 new papers a day, all over in all these different areas. It's because problems are really tough and there's a lot to think about.
Wait, 1,000 new papers?
Yeah. Turns out there's something like 500 mathematics journals that publish peer-reviewed research papers.
Okay, so I think we've sufficiently covered exactly what mathematicians aren't doing. But, what are they doing all day?
This is actually a really good question because as a former neuroscience researcher, I can tell you the exact steps needed in setting up an experiment, collecting data, and analyzing data.
But only applied mathematicians or statisticians would be researching in that style, right?
Correct. So, of course, I had to ask Benson.
So there's the mathematics itself, which is so many puzzles, so many mysteries, so much beauty and beautiful examples. But what you actually do all day, as a professor at University of Chicago anyway, and I think at most places, we might have a little less teaching, but it's still the same thing. You wake up, maybe twice a week, you have a class, which is wonderful. You have undergrads or grad students. But I come in to my office at 9 a.m. I will meet with PhD students. I have a lot of PhD students, so I have meetings with them, and we talk about their journey and the problem they're working on, and that could be for months and months or years. What should they be reading next? Where are they in the puzzle? They can bounce their ideas off me. But then a lot of time it's just me alone.
Oh, I would kill for some alone time at my job. Teaching 5 classes a day does not leave a lot of time to do the rest of my job.
You and me both. But to be fair, I think a sizable chunk of Benson's time is actually spent mentoring students and helping them progress in their careers.
Okay, so if pure math research is a lot of deep thinking, scratching out notes, and maybe not necessarily producing anything, how do you teach someone else how to do that?
You mean, how do you convince them that it's a worthwhile adventure?
Well, yeah, that too.
And my advice to my students and my undergrads is always try to find the thing that makes you giddy. It doesn't have to be in math. I mean, for the math PhDs, it has to be in math. But you should be giddy every few weeks. It doesn't have to be about your work. Just stay excited like that because it can be really hard. And so, but math is this infinite well of just incredibly beautiful, surprising, mind-blowing things. And at the end of the day, liking the lifestyle, liking the picture like I like, that's great. That can be inspirational like it was for me. But it's the math in the end.
So Benson mentors by helping his students find problems that get them excited?
Actually, yeah. That's exactly how he treats mentorship.
Sometimes people think I'm overly excited and kind of hurrah, hurrah for math. It's not at all. I mean, it's exactly because it's like hard a lot that you need those times when you're really excited. So I really just try to find things that excite them. And so I'll give them a bunch of kind of survey papers or papers and say, which of these things interest you most? And then it's like a tree. Mm-hmm. They pick one of the things and I'm like, did you like it? If not, then we do another one, but usually they like it. And then I'm like, okay, which sub-branch do you want to do? And, and you start talking to them about it. And then it starts to form. Most of the students like me to give them a problem. I don't have to, but I have with almost everybody. And that's like a strength of mine is like finding the right problem for the right person. And I try to always find something where they will be king or queen of their own direction.
What happens if the student ends up finding a passion that's totally outside of his mathematical wheelhouse?
Well, when I spoke with Benson, it sounded like he wasn't precious about expecting all students to love the same areas as he does.
Yeah, so when you start with a student, I'm trying, my whole goal is to try to find the thing that they will keep them up at night. I always say, I don't care what it is. And if it's not with me, if we don't find anything, that's fine. I'll help identify another advisor.
I hope most advisors are this supportive of their students.
Yeah, in areas like the biological sciences, there can be this temptation to keep students in your research group, even if it's not their passion, because they're providing a much-needed labor to actually run the experiments that you need for future grant applications.
I guess math research is cheap that way. It's not like you have to necessarily pay for a bunch of expensive equipment.
Just lots of chalk.
And don't forget the boards to leave in the hall where unsuspecting geniuses can solve problems.
But yeah, Benson always wants to make sure that his students are passionate about whatever problem they're working on. Because, surprise, surprise, math research is hard.
Math is really special because it's this incredibly hard journey that they're going to have to take. That looks impossible, that when you start the journey, if you keep learning at the same rate that you're learning now, it will take 100 years. So it looks like it's going to take 100 years, and you don't realize, no, your learning rate will double a few times, so it'll get down to 5 years. But it's really tough, it's emotional, it's like choosing a parent. It really matters.
Actually, there's a website called the Mathematics Genealogy Project that tracks the lineage of students and researchers as if it's like a true family tree.
Oh, that's so nerdy, and also I love it.
Well, for students to really learn a lot about their field of study and how to persevere, they can rely on their mentor relationships. I know I did.
It's the hardest time when you're a student because it's when you finally know. Like when you're second year, you do a year of courses, and then second year is when you finally realize how ignorant you are. You finally know how little you know. And you're at the point in your life where you know the least with that property. You have the property that you know how ignorant you are, and you know less. Like 6 months later, you also know how ignorant you are, but you know 6 months more of stuff.
Not much more.
Yeah, exactly. So I know that's confusing, but so it's sort of the hardest. So I had a really brutal time when I was a grad student.
Benson actually told current University of Chicago graduate students about his own struggles in grad school through a seminar series that they run on campus.
It's called Pizza Seminar. For the grad students run it. In the first 10 minutes, you do math, but then you could talk about anything. So some people juggled or whatever. So I just talked about my own grad school experience. And I was saying how I had severe depression. It was untreated. I had to go back to my parents for 6 weeks. I was not functional. Anyway, I had all my struggles. And then I did something in my thesis. And then I got jobs and I went to write up my thesis and it was wrong. I just thought, okay, I'll share that just in case. And literally for the next week, I had people emailing me, coming to my office, crying, thanking me, because they assumed everybody else, it was really easy for them. And of course, if you're a professor at Chicago, that your whole life was really easy. And since it's not easy for them, they're never going to succeed. And it was great because there was another professor there. And I asked him, did you have, and he had troubles too, as we all have. But if you don't know that, and somehow none of us expose ourselves. So that's one thing I learned too in advising, but even more broadly, just talking with grad students, to just expose my weaknesses and share my weaknesses. Because, I don't think it makes me a horrible person that I had all those problems, but I definitely think it's helpful to others just to know it's not the case that people are zooming through.
I've never been to grad school, but I can definitely relate to feeling like everyone else has their lives together while I'm flailing about. It's really great to be reminded that we're all just making it up as we go along, that we're all struggling in some way or another.
Yeah, grad school is really hard, and mathematics can be really hard. Being a mathematics grad student and just realizing how much you don't know and how far there is to climb, it can be overwhelming.
I know it helps my students a lot to reframe a struggle as a challenge that's worthy of tackling. And personally, it's taken a while for me to be okay leaving a lesson like, I know we didn't get this today, but we'll keep working on it.
Maybe you should have been the one talking to Benson. He said the exact same thing.
What I say to them is, you have this amazing opportunity. There's all these really smart people at Chicago, from the grad students to the postdocs to the professors. Some of the professors are really remarkable. See how far you can get. You made it this far. It'll be interesting. See how far you can go. You should go for the Fields Medal. And I mean it. Nothing's wrong with being ambitious. This weird thing everybody does it for the purity. Of course it's true. Of course we all love it. But nothing's wrong with being ambitious. But to me, my axiom anyway is growth. And so push, see how far you can go just for the fun of it.
Doing yoga has really helped me with this mindset. My teacher will walk us through some crazy pose and I'll think to myself, nope. But she's created an environment where I feel comfortable just trying, even if it means I fall. And because of that, I'm able to do things now I never thought I could.
Well, should we hear one more piece of mentoring advice before we take a break?
Of course.
When I asked him about how students can overcome this hardest part in their education, he said to just ask questions and not be afraid of looking stupid.
Ever been afraid of asking? And the people I see fail, it's invariably people who are afraid of looking stupid, so they don't ask the questions. When my daughter was younger, she didn't want to look stupid, and she would say, I knew that, I knew. And I was really worried, because if you're not willing to ask questions, you're probably going to fail, unless you're one in a million. Of super original thinkers who don't need anybody else, which I don't even know if they really exist. But and I remember, I think it was 8th grade, my daughter, for some reason, something clicked in her. And she was totally willing to look stupid. And I thought, I'm not worried about her anymore.
I can't say this is a surprising piece of advice. Honestly, this is the biggest indicator of success in my students. Like, are they comfortable enough to make mistakes and look stupid? And it's definitely part of my job to create a space that supports that, which often results in me acting stupid and making mistakes left, right, and center.
Right? It feels so obvious, but I still think it can be really hard to do.
As a white male, no one's questioning my authority. So I can definitely see being more fearful of looking stupid if people are already questioning me when I'm looking smart.
Yeah, very true. It's a lot easier to make mistakes when you know there's the safety net our privilege has allowed.
This gets into a whole field of psychology on stereotype threat that I actually think we should save for a future stats episode. So why don't we take a break and then come back to discuss the big topic we skipped over?
What Benson actually studies?
That, and how he got roped into mathematical research to begin with. Can I start by just saying that Benson has a very funny way of setting up his stories?
What do you mean?
He's just got this comedic sense that's really refreshing. Here, let me give you an example from when I asked him how he got interested in mathematical research.
I was taking, I think it was 10th grade, and I took this math class. It was like Algebra 2, one of those kind of courses. And I remember I got like a D on my first math test. And what it was, I would just do the hardest homework problem, and that's it. And if you just do the hard stuff, that's not a way to actually really learn the ins and outs and get a feel. And so I got a D, and I was really upset. And after that, I did all the problems in the book, and I got another book and did all the problems in that every time. And so I ended up winning the math prize that year.
That doesn't seem funny. It just seems impressive.
Hold your horses. We're getting there.
So I had won the prize, and then I wanted to thank my teacher. I went to his classroom after. There was like the last day of school and the prize ceremony. And he went to the bathroom. Another bathroom-related thing. My life is controlled by. And I'm not kidding. I randomly pulled out a book from his bookshelf because I was waiting, and I have a short attention span. It was this Time Life book from the 1960s, this old Time Life book they had in life, in physical and life sciences, this series of books. And it was one on mathematics. I opened a page, and I see a guy lying on a bed. There's a statue of a naked woman. Sorry. It's African art, actually. And it's this amazing photograph, and you see the shadow. And I'm like, what is this? And the guy's just open eyes on this bed, staring into the distance. And it says underneath, Professor Samuel Eilenberg sprawled out thinking about math. And then he's quoted as saying, yeah, I usually think about math on the subway. And I'm thinking, what? My professor explained to me, my teacher, I don't know how he knew, but he had some books on this. There's something called a pure mathematician. They just think about math problems all day. There's some teaching sometimes if you're a professor, but that's only a few hours a week. But mostly you're sitting thinking like that. And something about that photograph. This is ridiculous. You'd think it would be the mathematics.
So is he saying that a teacher's bathroom break altered the trajectory of his career?
Yes, but this was actually the second time that Benson mentioned having the direction of his life utterly changed based on a decision to go or not go to the bathroom.
One little decision changed my life, and I spent 3 years at Berkeley. But not officially, just hanging with my advisor. But then I met my wife. Everything changed for me on a decision to whether or not to pee, actually. It was the most important decision of my life. I was studying something called homotopy theory and K-theory. I went to Princeton to do that. And I was working with a guy there named Wu-Chung Shang. And I was hard at work in my first year, near the end. And in this big tower called Fine Hall Tower, I walked the stairs down. It was 6:30 at night. I remember it like it was yesterday. I was 21 years old, and I opened the front door and felt the wind on my face and realized, gee, I have to pee. Can I make it the 5 minutes to my house? We've all made that decision. Or should I do it here? And who knew that was going to be the most important decision of my life? And I decided, oh, I better stay. So I closed the door, went to pee. It took 2 minutes. On my way out, I ran into a visiting mathematician who had made an extra copy of a paper. In those days, still Xeroxing, so he made it from one-sided to two-sided, so he had this one-sided copy. And he said, I made an extra copy. Do you want this paper? Now, it was nothing to do with my area of mathematics, but in those days, I would collect papers because, you couldn't get them on the internet. And I took it home. I read it. It inspired me. It was called Sur les groupes hyperboliques d'après Mikhail Gromov, so I pushed through the French. Totally inspired me. I totally changed my philosophy of mathematics. I switched advisors because there's only one guy at Princeton who worked on this kind of stuff. His name's William Thurston. He's probably the greatest geometric thinker in history. And that changed my life because I changed mathematical fields.
Okay, I see what you mean about his comedic sense of timing.
Yeah, I mean, he still could have ended up in math through another trajectory, but in a lot of ways, it just came down to luck.
And curiosity.
Right, and definitely curiosity. Curiosity is what drives him to constantly be switching areas.
Oh, it's been a continuous movement ever since. I like learning new things, and I'm always a beginner, which is always terrifying.
Oh, yeah. Wait, how have we gone this long without talking about what Benson actually studies? I mean, we heard about what a mathematician does all day, but what does he specifically think about?
How did we manage that? Well, after Benson followed Thurston to Berkeley, he ended up in a field called geometric group theory.
In terms of career, it was like the right place at the right time. It was like perfect for me. I was able to make much bigger contributions than I ever would have in my original field. There's no question about it.
And geometric group theory is?
I would just say it's the study of symmetry and using symmetry to understand and simplify the understanding of complicated objects. And that's definitely used in physics all the time. When you hear about that they know of 3 particles with certain properties and they're predicting the existence of 2 more. Like, what in the world does that mean? And what it means is purely mathematically, not informed by any experiment. And I love doing this when I teach my undergrads. I start doing stuff on the board and I tell them, I'm going to do stuff, no experiments, purely from our mind. I'm going to prove that this kind of math object has 5 kinds of symmetry. And that describes these particles in nature. And we've seen 3 of them with exhibiting 3 of the different kinds of symmetry. And so why would God have, I don't believe in God, but why would God have picked those 3? That's why they predict there should be 2 others exhibiting the others. And so the universe follows our rules.
But like I said, Benson is really driven by curiosity. He doesn't like to settle into one area or field or subfield. He's constantly jumping into new areas.
I like being they say if you really want to make a contribution, you can either be the first or the best. And it's easier to be the first. A lot of people say that. And that's a little bit true, but it's more just I'm driven definitely by curiosity. And I only want to do, this is what's great about the freedom of tenure, do what I think is, but I still like to do what I think is important, but definitely fun and exciting. But also I feel like I want to do something I think is quote unquote important in the context of theoretical math. I don't pretend that what I'm doing but I have to pretend to myself that what I'm doing is important. I don't even think it's necessarily important in mathematics. I need to think that it's worthwhile doing. And that's often the case that others don't.
So what happens once he's learned enough in a field to make a few contributions?
Well, then it's time to move on.
Sometimes I've made new connections, and then other people get interested. Then a flood of people come in, which is great. They prove much better things than me, because that's not my strength, and they get really sophisticated. And then I feel like if I want to continue and be a serious player, I have to learn all this stuff, and then I move.
And I know we're painting a bit of a clean picture here.
You mean that Benson gets curious about a topic, does some publishing, and then jumps to a new one once he's been successful?
Exactly. And we spent the first half of this episode reviewing how it's so hard and frustrating to be a mathematician sometimes, that often you work and don't necessarily produce anything. That's true for Benson as well.
Hardest problem I've worked on, which was over like a 7-year period, I'm still working on it. I have about 800 pages of notes. 0 of them are published.
Girl, you better push that boulder up that hill.
Sisyphus reference, huh? Okay. But somehow Benson is still quite positive about his failed attempts.
In failing, you learn. It's a kind of unity of mathematics. I had to learn how geometry has to do with equations, has to do with symmetry, has to do with curvature, has to do with matrices, and it's all one big picture. And the point of view of older mathematicians from the 19th century and things that we've forgotten, and I've given talks where I just explained some 19th century stuff to people, and they're blown away by it. And so that's all quote-unquote success in my book.
It must take a special kind of person to keep hitting a brick wall like that and still want to try and figure out the answer.
Yeah. I mean, researchers from all different fields well outside of math also talk about the frustration of trying to solve a problem by just throwing everything at it. But I will say, in most fields, there is actually a solution or answer that can be found.
And that's not true in mathematics?
Well, it depends on the area. For Benson, he likes the unknown.
And I also like things where you don't know the answers. That's the kind of problems I like. Even some of the most famous things, like Fermat's last theorem, definitely one of the great achievements in the history of math, but they knew the answer. They're trying to prove that the expected thing is true. There was an expectation. Certain kinds of equations have no solutions. And then in the end, he proved that. So it's an amazing piece of math, but there's stuff I'm working on now is about what are called K3 surfaces. They actually occur in string theory a lot, and I'm looking at them with a guy, Edouard Loyenha, for the last few years, and we're trying to understand topological symmetries of these spaces. Again, it's some kind of a symmetry, but where you can bend and stretch. But the point is that we don't know what we're trying to prove.
Don't know what you're trying to prove. Yeah, I'd say that's solidly in the realm of the unknown.
Right? And it's kind of funny because Benson's work on symmetries actually has a lot of applications to fields like chemistry or physics, but he totally doesn't intersect with those people at all.
I teach a bunch of chemists because they do symmetries, especially finite symmetries, because you want to know, like isomers are you want to understand reflections.
I was going to say chirality, right?
Chirality, yes. But so it's funny because a lot of the objects I study are studied by physicists, although string theorists, I don't know if physicists would call string theorists physicists. No, but whatever. So for me personally, I'm embarrassed to say, I have not collaborated with anybody outside of pure mathematics. I would say I'm pretty broad within mathematics, but that's like an ant saying he's got a really big house, I guess.
Yeah.
I have a really big ant house. And it's not that I wouldn't want to do it. It's just the things I'm interested in are a little further away. A lot of things I'm studying have so many instances within physics, but I don't actually care about any specific physical system. Like, I spent many years and I still study kind of configurations of points moving around into space. So it would be like robots on a factory floor or satellites orbiting the Earth, or airplanes in the sky. So you have, say, 10,000 airplanes and you're registering their height, longitude, latitude, altitude, and speed. Mm-hmm. So that's, let's see, 10,000 airplanes and there's 4 coordinates each. So that's 40,000 numbers at any given time. And now over time, those 40,000 points are moving inside some 6-dimensional space. So I'm answering questions about that. All those or you can have atoms of a gas that you
like
release
Brownian
into a room,
motion, right?
Brownian motion. But I'm studying like the space of all those things. I'm motivated because it's just super beautiful, and it has to do with fundamental mathematical objects like equations, polynomials that we've been studying for 3,000 years.
So Benson's math does have applications, but that's not his driver.
Because his main motivation is his own innate sense of curiosity for the math itself. Kind of like spending hours practicing a piece you may never play for anyone. You're doing it for the sake of doing it.
To be fair, if we take a historical perspective, curiosity-driven mathematical research has led to all sorts of important inventions that we take for granted today.
The mathematics that we were doing in the 18th century, 19th century, that was just because it was beautiful and fundamental, that is often used for the most concrete things. Having today, from cell phones, you wouldn't have a cell phone, you wouldn't have computers, you wouldn't, just every single thing uses mathematics that seemed very abstract. Like you take Hilbert space, that's like an infinite dimensional, like what are you talking about? Infinite dimensions. This was like in the late 1800s, maybe 1900. And, but without that, you wouldn't have the transistor because you wouldn't have quantum mechanics. You wouldn't have the transistor. You wouldn't have computers. So that's a pretty important thing. Even though it sounds like infinite dimensions is some abstract thing, literally you use it to make calculations. So sometimes I say, well, maybe the math I'm using will be used in hundreds and hundreds of years. But to be honest, I don't really care. I'm doing it because it's beautiful.
What a wonderful nerd.
Takes one to know one. But yeah, I'm glad we have mathematicians like Benson here at UChicago who keep pushing the boundaries of our knowledge, even if it's never clear where we're going with it. And don't forget to check out our show notes in the podcast description for more about the University of Chicago Math Department and further resources on additional topics we covered today.
And if you like the show, give us a review on Apple Podcast or Spotify or wherever you listen. By rating and reviewing the show, you really help us spread the word about Carry the Two so that other listeners can find us.
And for more on the math research being shared at IMSI, be sure to check us out online at our homepage, imsi.institute. We're also on Twitter at IMSI_Institute, as well as Instagram at IMSI.Institute. And that's IMSI spelled IMSI.
And do you have a burning math question? Maybe you have an idea for a story on how mathematics and statistics connect with the world around us. Send us an email with your idea.
You can send your feedback, ideas, and more to sadiewit@imsi.institute. That's SADIEWIT at imsi.institute.
We'd also like to thank our audio engineer, Tyler Damme, for his production on the show. And music is from Blue Dot Sessions.
Lastly, Carry the Two is made possible by the Institute for Mathematical and Statistical Innovation, located on the gorgeous campus of the University of Chicago. We're supported by the National Science Foundation and the University of Chicago. Oh, I was going to tell you. When I was hosting with both Carrie and Jude, both times they were like, Tyler Damme. Tyler Damme. And I was like, Dammy. And they're like, damn, I thought that was it, but it couldn't be right. Just all of this will be getting cut. 1,000%.
Is this really...
Also, of course, it's Benson in my head. Every time I was writing this, I was like, Benson Hedges, Francisco.
I don't know that.
It's a joke name for Jensen Ackles to mess with me.
Oh.
The Benson burner.
Sorry, the Benson burner.
Burner.
The Bunsen burner, Benson burner. What was I doing when I wrote this?
All right, Choo-Choo, I hear you.
Girl, you better push that rock up that hill. Benson. I don't know what you're trying to prove.